This second slide set introduces us to the formation of sedimentary rocks. If you recall, last time I said that sedimentary rocks were the most important rocks for us in this class, and this slide explains why. If you look at the world as a whole, the globe, then igneous and metamorphic rocks, well, that's 90% of the total volume. So you would think that, okay, those are the most important. But if you look at the surface of the earth, where we live, where all of humanity has ever lived, where all living things ever on planet Earth have lived, 80% of that is covered by sedimentary rocks. So if you understand sedimentary rocks, you have the history of life on Earth. All right, we start with the whole notion of weathering. And weathering is just a simple way of saying the whole suite of processes that take place on the surface of the earth between air, water, living matter, etc. It is the first process that we think about when we're talking about making of sedimentary rocks. And then there's, of course, a straight definition of it, breaking down of any pre-existing rock into future sedimentary rock materials. Well, there's two flavors. The first is called physical weathering, and that is literally just breaking a rock into smaller and smaller and smaller pieces. The picture you're looking at is a famous boulder in Yosemite National Park, and it rolled down the hill, and you can see a prominent crack in it so that one half is there and the other half is there. It's one rock, it's one clast, but it has been broken into two. Now, you haven't changed the chemical composition at all. The only thing that's happened is you've reduced its size, and that's the most common type of weathering. This slide is a mountaintop in Nevada, and you can see on this mountaintop right here all different boulder sizes, from very large ones to smaller ones, medium-sized ones, and if you were able to zoom in, you'd see all of this, even more, just solid. These are all clasts. If you look at them, they have, in the slide, they have similar colors, similar looking textures. They're all the same rock type, the chemical composition. They've simply been broken into smaller and smaller pieces. This is another slide. This is from the Canadian Rockies, and you can sort of see over in the lower right area some people hiking across a trail over here. But the important part that I want you to look at is the mountainside in the distance. You see the big cliff face, some snow at the base of it, but then this big mound of debris at the bottom. That's the scree, the stuff that weathers off and breaks off. And again, that's all these tumbled down pieces of physically weathered material. When I tell students to look at this slide, I tell them, imagine that these are gravestones. And if you look at it, you don't have to necessarily do the math on this, but if you have something that, let's say it's 2 feet by 2 feet, so it has 4 square feet exposed here by area, so length times width, and then the 6 sides for the cube to get 24 square units. Well, if you take a hammer to it, a big sledgehammer, and bust it up, and miraculously it breaks into these 8 little cubes. Notice it's the same thing. It's the same rock. It's made of the same thing, but you have broken it. You've taken this big clast and made it to a bunch of smaller clasts. And you can bust it again with that sledgehammer and make a whole bunch more. And see, one thing you notice here, the square units, that's the sort of surfaces available, increases the more you break this down. So physical weathering has this effect. It breaks things down, composition stays the same, but the surface area, the area that's exposed to, well, the weather, increases. Which brings us to the second type of weathering, chemical weathering. And chemical weathering is a whole bunch of other things, but generally for us in geology, it is dissolving. Here you're looking at the top of a mountainside. There's a person standing sort of in the distance there, and you can see a pool of water on here. And water has acted on this rock over many millions of years, and it's dissolving it slowly but surely. We don't really think of water dissolving rocks, but given enough time, it does that. And so the water sitting here causes chemical reactions to literally dissolve the rock away. That is the chemical weathering. And chemical weathering makes different looking results. If you remember the slide of the mountainsides in Nevada and Canada I showed earlier, there were a lot of jagged angular pieces, evidence of physical weathering. Look at here, you've got this person standing here in the lower right, and this is from Joshua Tree in Southern California. It's a famous hiking, rock climbing area. Notice here, all of the rocks have smooth, etched, rounded surfaces with curvature to them. This area is being chemically weathered. This rock is slowly sitting there, and the elements are weathering it away. So when we think about weathering, we think of it in terms of two different products. The physical weathering, or PW, produces what? Smaller and smaller pieces. We call them clasts or sediments. Chemical weathering, the other half of the weathering 1-2 punch, dissolves things. And so what it produces is free atoms after the existing chemical bonds are broken. Those are the products of weathering. Now, look at this slide here. This is, it's very complicated here, but just think of it this way. You've got a mountainside here, and you've got some arrows coming out of it. You can see the broken physical weathered clasts at the base of this thing, but realize that this is also, every time it rains or snows, it's going to wash out and produce chemical weathering. This is the first in our set of steps to make sedimentary rocks. After weathering, what happens? Well, they move. So these blocks roll down a mountainside. Maybe a river floods through here. It moves this way. The dissolved ions go this way. They are eroded. So the very next step after being weathered is erosion and transport. And on planet Earth, we have three things that do that. We have water, wind, and ice. Water is the primary one, but of course wind, if you've ever been in a dust storm, a sandstorm in the desert southwest like Arizona, you know that wind can certainly pick up and move a lot of things. And then ice, glacial ice. Glaciers act like giant bulldozers going around the globe or around the mountainside, pushing everything in front of it. But that doesn't go on forever. Water doesn't flow forever. Wind doesn't blow indefinitely. Ice stops. That brings into account the next step, which is deposition. Deposition simply means the place where the clasts are all stopped, or the free ions are stopped. And we say that this is done in a basin. And the ultimate basins on planet Earth are the ocean basins. Think about it. The Mississippi River flows till it reaches the Gulf of Mexico in the Atlantic Ocean. The Amazon River flows until it reaches the Atlantic Ocean, etc. And when they deposit, when these clasts and sedimentary free ions are laid down in these basins, they're laid down as flat things we call beds. That's still just a pile of clasts. It's still not actually making sedimentary rock. The last step here, lithification, can take millions of years. But that's where you take loose sediment, like the sand that we talked about in the very first lecture, and squeeze it and cement it, rebond those chemical elements that we dissolved away with chemical weathering, and make a solid rock again, making sedimentary rocks.